Okay, folks, we're going to start. Good morning, everyone. I hope we've had a great weekend. So before we start, I have a few administrative items we want to go over just to make everything smooth with the course. So if you are in a team of 3, that's great. Your CI/TA meeting rooms are all posted now on Quarkus. You should be able to find them there. Your CI will email you this week, if they haven't already, to schedule meetings for the rest of the semester. So you won't be meeting the CI this week, but expect an email from them. For the lab rooms, you should know your assigned TA on the Quarkus, and then go to the lab room that's also assigned for you. If you're not in a team of 3, that's fine. You can meet Dr. Chong in the first hour of your tutorial this week, or if you received an email, please go there as well. So anyone who's not in a team yet, or if you are a team of 2, or if you received an email from Dr. Chong, please go to the one of these rooms based on your tutorial time slot in the first hour of the tutorial. So on Monday, 10 a.m. right now, after this lecture, go to BA 2145. At 3 p.m. today, go to BN 2145 as well. Thursday, 4 p.m., go to BA 2185, and Friday, my hall, 3:30 at 4 p.m. Okay, Professor Chung will try to basically either complete your team or put you in a team of 3 if you haven't found any teammate yet. In the meantime, if you've decided that you want to go with a certain group or you've formed a group of 3, please email Dr. Chung and I your user IDs so that I can register you on the UG machines and you can start coding immediately, and we can assign a TA and a CI for you. So you don't have to wait, like if your tutorial is on Friday, you don't have to wait till Friday, you can email them before. For the tutorials, basically today's tutorial will cover milestone 1 and will try to solve one of the functions required in milestone 1. So it's a really important tutorial to let you know how to basically tackle this milestone. The same tutorial will be given twice, one in the first hour and the second hour. So feel free to go in either the first or the second hour of your tutorial time slot. And from now on, basically all tutorials will be held in BA 255. Okay, for milestone 0, the submission is closed on Friday. I've allowed some students to demo TAs to demo today. So last day to demo to a TA is today if you haven't done so. If you have, then you're all good. You don't have to do anything else. Okay. So now that milestone 0 is over and hopefully you've learned some of the tools that we're going to use throughout the semester, the real fun begins now. Milestone 1. Milestone 1 is released. It is due Saturday, February 8th. It's worth 10% of your mark. And from now on, basically, you're going to work with your teammates to do all the technical and non-technical milestones. Okay. 7% of those 10 will be auto-marked by our public and private tests. The private tests are basically additional tests to the public ones. They are kind of the similar ones. We're not going to trick you. They are not more difficult, but they will probably cover more corner cases that are mentioned in the milestone 1 handout. So read the milestone, the handout carefully. Make sure that you've covered all the corner cases for all the functions that we need you to run. Some of those tests are for functionality, so they will basically test the robustness of your code, whether they meet all of the requirements, and some of them are for performance. Basically, do they run in a timely manner? Because some of them will require you to write more more advanced data structures, similar to the ones that you learned in the first 2 tutorials from the STL library, so that you can basically let your code run faster. And in the handout, we basically mention whether this function will be tested for performance, or whether it's moderate performance, or whether no need to test for performance for this one. The other 3% will be marked by the TA after you submit your code. Basically, they will go over your project management. If you recall from lecture 1, we've talked about that you're going to have a wiki page where you summarize your progress, how you divided tasks across your teammates, and your TA will basically go every week over that page to see whether you are managing your project well. They want to make sure that it is well summarized. You can add as many details as you want, but like I prefer to add a section on top of the page for only the TA or the CI to look at, so that they don't have to go into the details and just get to the point where they to know the stuff that they need to know. Other stuff they will be marking is the coding style. Are you using good variable names? Are you indenting your code well? One of the tutorials in a week or two will basically cover what is a good code style. So I also recommend attending that one. Git usage, are you basically, is every teammate doing commits regularly? Are the log messages or commit messages meaningful? So the TA will go over all of that to basically decide what mark to give you. This mark will not be common to all three team members, so expect also the TA to ask you questions when you demo them after the submission. Deadline they will ask you any question regarding the code, like who did this, how did you implement this function, etc. I've posted, in addition to the instruction, I've posted a rubric to let you know what kind of stuff the TA expects, so that you try and cover to cover most of the criteria. Okay, any questions so far regarding these administrative items? Nope? Yes?
I think you had Tuesday tutorial, it was Monday 3 to 4, I think that's Tuesday.
Oh, that's the lab, you're correct, sorry. So the second one is Tuesday from 3? Yeah, okay, so 3 p.m., sorry. Okay. So now I'm going to go dive into a little bit of the details of what you're to expect in milestone 1. I'm going to give you an overview of the data and the APIs that you're going to use to tackle milestone 1. So in this milestone, or in this project for the rest of the semester, we're gonna use real data of various cities around the world from an organization called OpenStreetMap. OpenStreetMap is created by regular people who like mapping stuff and basically volunteer to enter data about any city in the world. And it's a very big data that's posted online and basically reviewed by peers, so that they make sure that the data is correct. Actually, you might see various websites or programs that have a little copyright or acknowledgement of OpenStreetMaps. It's basically used in lots of open source or commercial endeavors that is related to mapping. Okay? So how's this data organized? I'm going to tell you first how the raw data looks, and like the ones that you find online. And then we're gonna talk a little bit about some of the data that we've organized a bit more and made it easier for you to understand. So the raw data basically consists of 3 types of entities. And each of these entities is basically identified by a globally unique N64 integer ID called the OSM ID. By unique, I mean that there is no other point in the surface of the Earth that has the same ID. So every entity or every point on Earth has a ID only specified to it. So you can basically identify it and get any of the features that are related to that point on Earth. Okay, so the 3 types of IDs are the 3 types of entities are basically, the first one is OSM node. A node is a very simple entity. It just basically represents a certain point with a latitude and a longitude on the surface of the Earth. So, for example, my hole has an OSM node that's associated with it, and it has an OSM ID that identifies it. Okay. On top of this latitude and longitude, there can be certain other, we call them tags or attributes associated with that OSM entity or OSM node that basically represent key value pairs. I'm gonna talk a little bit about them. The second type is called OSM way. OSM way basically is a list of OSM nodes, or a collection of OSM nodes or points that represent a path or a street, for example. So it can represent a piece of road, a shoreline, a park boundary, etc. And the third one, which is the more complicated one, is called OSM relations. And OSM relations is basically a group or a collection of all of the above entities. So it can be a group of multiple OSM nodes or multiple OSM ways or even relations. So, for example, a big park like Hyde Park will be represented by an OSM relation that consists of multiple smaller OSM relations, because there are streams, there are ponds, etc. inside the park. So each one of these is called an entity. Okay, so as I mentioned earlier, basically there are optional tags or attributes associated to these entities, and these are represented as key value pairs. Basically, for example, an OSM way can have a name, okay? And that name will be, the value of that name will be Young Street, for example. Or a certain feature will have a natural attribute, and that feature will, and the value for that feature, natural attribute will be water, for example. Okay. So all of this is documented online and it's open source. Anyone can contribute to this data, and it's basically on this wiki page. People contribute to it all over the world. But as I said, this data can be really big. It can be downloaded for the whole planet in an XML format. XML is basically, if you haven't heard of it, it's like a text file format that is a human readable, and it makes it easy to understand basically what each city consists of. Okay, for example, the file for the whole planet is bigger than 1 terabyte, and processing this data might be really slow and very inefficient. Okay, it's very hard to work with. So we have extracted and downloaded several cities for you to work with. So you don't have to basically work on the whole planet at once. For example, we've extracted the maps specifically for Toronto, or specifically for I don't know, Berlin, London, New York, etc. So this is an example, of how the Toronto, Canada file looks like, the XML file. And just a second. And if you can see here, for example, this identifies here a node with a certain 64 integer, and this node has a latitude and a longitude. Okay, another entity is basically a way, and it also has this ID. And it tells us that basically it has this tag, so it's telling us that this way is a highway, basically, it's part of a highway. Okay, but even for Toronto, Canada, the file size is 1 gigabyte. So we want to make it smaller to make sure that we are able to quickly or efficiently work with it. So some of the trade-offs of the OSM data the positives are basically they're very powerful. With only 3 entities or classes, we can represent any city in the world. It's XML, so it's basically human readable. It's very easy to understand. The problem is that the data is very low level, so you need an expert in the maps to basically be able to interpret these data. It can be somewhat inconsistent because anyone in the world can enter data, and although it's peer-reviewed, you never know, it's very error-prone. Someone might enter the wrong data. It's very big. For example, the Toronto map is 1 gigabyte. So it's very slow to load. It takes around 45 seconds to load a 1 gigabyte file and try to parse it in memory. Okay. So what is the solution for all of this? We've created a program specific for this course called OSM to bin. And its job is basically to parse, reduce, and refine. What do we mean by that? So it basically reads the raw OSM data that we've showed you before. Okay, and it applies some consistency checks on it. Basically, we make sure that all of the data makes sense or everything is correct. We organize the data in some way that makes it more efficient, and we omit the stuff that we might not need. And then we write out the essential data in a binary file. A binary file is basically a file of ones and zeros, so you probably won't be able to read it. It's not human readable, but it can be loaded through 2 of the APIs that we provide you. I'm going to talk about them in a bit. One is called Street Database API, and the other is OSM Database API. Both of these APIs are going to be your friend for the rest of the semester. And it's much smaller in size. Now the file size is decreased from over 1 gigabyte to only 93 megabytes. 93 megabytes is very good to work with because now we can load it in around 1 second in memory. to initialize the same classes. All of this process, which is parsing, reducing, refining, is called class serialization. It's a very well-known technique when working with big data. Basically, the job is to load the data in memory, parse it, and try to clean it up, and then use a library that can write this data to a disk so that you can efficiently read it back again later. You can do this manually, basically, and the job will be done. But the problem is it's very error prone. You might forget how you parse the file, so next time you load it, you might not be consistent. So we usually use libraries that do this. In this course, we use a library called the Boost library, and what it does is basically read the data, all the classes that we have in memory, and just try to write them in to a file in a very efficient way. The next time we load our program, we just call this library again, and it will basically load our data in the same way that we had it before writing it out. So all of this is done in the background. I'm just telling you so that you know how this is done. So you don't need to do this for this course. However, if you prefer for the future milestones to add some of the maps that we haven't added for you before, you can download them from the OSM data and then use this program OSM to bin to basically serialize it. Okay. So milestone 1 is all about API layers. API means an application programming interface. It's an interface of functions, a header file that you talk to so that you can answer questions about the underlying data. You don't deal with the data directly. As I mentioned before, basically all of the data is organized in the main file called the Toronto OSM, for example, and then we've extracted for you two types of files. One is called torontocanada.streets.bin, and the other one is called torontocanada.osm.bin. The .street.bin is a more organized data, and it organizes the city into streets and intersections that is easy to deal with. Most of your code for milestone 1 will deal with this file. The other one, which is the binary file, the osm.bin, is basically less organized, and it contains all the stuff that you might need for the rest of the semester. We've only removed the data that we are sure that you don't need. For example, someone added a timestamp when they added this data. You don't need that. So it is still a smaller size than than Toronto.osm, but it is less organized than the streets.bin. To get you used to this data, we've also require you in milestone 1 to write two functions that will deal directly with this data. Okay, so as I mentioned, basically you're gonna work with APIs. So we have two APIs, the Street Database API and the OSM Database API. Both of these APIs talk to the underlying data. The main one, we call it layer 2. You're gonna use it heavily in milestone 1, and this talks to the .streets.bin file. And the second one, OSM Database, it talks to OSM.bin. This is the more detailed one, less organized one, and this is the first layer of the APIs that you're gonna deal with. Okay, so all of that is given for you. So what do you need to do in milestone 1? In milestone 1, you're gonna build your own API, and that you're gonna use for the rest of the semester. This API is called libstreetmap. And we provide you with a header file called m1.h. m1.h is a readable only file, so you cannot write to it, you cannot change it, and it specifies the functions that you need to implement in order to pass the test for milestone 1. Okay? It's very well commended. It will tell you exactly what you need to do for each function. Again, how to use it. It will not tell you the implementation. You need to write the implementation. So under libstreetmap.source directory, you're going to add as many CPP files as you want. You can write them in one file. You can write them in multiple files. I usually prefer to divide my work into multiple CPP files so that each file is related to a certain type of functions or classes. So here is an example. We just call them m1.cpp, helper.cpp, so that you can, for example, add helper functions that you need. Okay? So to implement these functions, you're gonna call functions from both APIs to answer questions about the underlying data. And you're gonna organize your data in an efficient way so that you can pass the performance test as well. Any questions so far? Okay. so now that we've talked about an overview of what data you are using, let's jump into describing what these lower level APIs that you will talk to look like. Okay, I'm not gonna go into too much details. All the details are in the M1 handout. Both of these APIs, or the header files from these APIs, are also written in the M1 handout. So read it thoroughly. It basically describes everything that you need to know to complete the milestone. Okay, so first of all, before jumping into details, what will we do with this data? In milestone 1, as I said, you will use the provided APIs, mainly the street database API and the other one, to implement various functions. For example, this is one of the functions that you need to implement. It's called find street names of intersection, okay? And it's the comment above it, it basically tells you that you need to return the street names at a given intersection. And for example, the speed requirement says high. So that means that this function has to be really efficient in order to pass the performance tests. Some of these functions, or most of these functions that you will write in milestone 1 will stay with you for the rest of the semester. So don't throw away your code. That's why we use Git, because we might need to use them again for future milestones. For example, in milestone, you're gonna build on top of your API in order to visualize the maps that you're working with. In milestone 3, you're basically write some algorithms to find routes between 2 points or 2 intersections, for example, and then visualize that as well. And in milestone 4, it's basically a more open-ended problem that we're gonna talk about at the end of the semester, but it also builds on top of your libstreetmap API. Okay, so how is this data represented in our APIs? Anyone heard of graphs before? Yeah, a few. So a graph is a more complex data structure that you've probably haven't studied before, and it represents the connectivity between items. The items can be anything, and basically it represents which item talks to which item. So usually a graph is represented with 2 types of entities or data. One is called the vertices or node. We usually call it V, a set V, and the second one is called the edges, and basically it represents like how 2 vertices are connected, whether 2 vertices are connected or not. Okay, so any graph you will see will be represented by this notation, which is basically tells you that it has this set V and this set E. Okay, so what is a graph? You've already probably used special cases of graphs before in 244, for example. For example, a linked list, each node vertex only connects to a previous and next node. So basically, here is a vertex or a node, and there is another vertex, and there is an edge between them that connects basically this next node to this one. At most, there are 2 edges per node in this graph, because you can also connect to the previous node in a doubly linked list, which is more common. Another type of data structures that are special cases of graphs is the binary search tree. Each node basically connects to 2 children, and so again, there is at most two edges per node. There are certain types of binary trees that also talk to the parents, so you can also have more edges that go back, okay? But a more generalized graph, you can have as many edges at a node as you want, so it's very arbitrary, and there is no special cases to handle them. Okay, so this is an example of a graph. Basically, there are 6 nodes or vertices in this graph, and for example, node 1 has only 2 edges connected to it. It connects to vertex 2 and vertex 3. For example, node 6 has only 1 edge, and node 4 has 3 edges. So it's very arbitrary, it's not uniform across all vertices. And this is what we're going to use to represent our maps. Okay? Graphs are really important data structures that you're going to encounter a lot in any complex algorithms that you're going to write in your future. If you want to learn more about graphs, basically there is this popular book called Introduction to Algorithms. It has several chapters on how to write graphs and what kind of algorithms that deal with graphs. You will probably learn more about them as well if you take ECE297, which is data structures and algorithms, next year. And in this course, we'll cover some of the most important algorithms that you need to understand to basically do your milestone 3 and 4. Okay, so we've decided that we're going to use graph, but now we want the more important question is, what should our vertices and edges are? Anyone can guess? So how are we going to represent our data? B07, just a second. Oh, sorry, there is C02 first. What is C02? BC, there you go. C02, did you press on purpose or no? Doesn't look like it. Okay. So B07. Go ahead.
Intersections and streets.
Intersections and streets. So what are the intersections going to be? Okay, yeah, so that makes sense. Basically, meet me after class, you're going to get a chocolate bar. This is a tough question. So basically, the intersections in any city will represent the nodes of our graph, and then the streets will represent the edges. Now, the thing with streets is basically they can go across multiple intersections. So to make the data easier, we divide these streets into what we call street segments that we're going to talk a little bit. Okay. So again, the V is the vertex in the graph is the intersection, and then the street segments or city blocks will be the edges. Okay, so here is an example. Again, for example, this is College Street. College Street can span across multiple intersections, which makes it complicated to represent our data if we're going to use the whole college as the whole College Street as an edge. So we divide it into what we call a street segment. A street segment is only a portion of the street that connects two intersections, and it is very easy to model because in most cities across the world, they are represented as city blocks, so the intersections basically will be connected through one edge. So for example, here is a street segment that connects two intersections. Okay, so how do we identify each vertex in our city? So part of the OSM to bin executable that I talked about earlier is that we've worked out how many intersections are in each city and what edges or street segments connect each intersection. And we've uniquely assigned IDs and represented the data in a more abstract way so that you can understand it. Okay, so the first thing that we've extracted are the intersections. Each intersection is uniquely identified by an integer ID. Don't confuse that with the OSM ID that we've talked about earlier. OSM is unique for every node across the surface of the Earth. This is unique only in the city that you are working with. So if you loaded Toronto City, this integer ID will be unique only to this. And in each city you're going to load, part of the street database API, there is a function called getNumIntersections. This will tell you the number of intersections that are in the city, and each of these intersections is uniquely identified from 0 to get intersection -1. For example, in Toronto, there are around 190,000 intersections, so the intersection will be, IDs will go from 0 to 1899999. Okay, so on top of the integer ID, there is also a string associated with that intersection. It's basically the string gives it a name. So it may not be unique for all intersections. That's why we only rely on integer IDs to uniquely identify these intersections. Plus, integers are much smaller to deal with in terms of size than strings. So the string names are mostly used for user output or when you visualize your data in the milestone 2, for example. So an example is like Bloor and Young. That's a name of an intersection that you're probably gonna find in the map. Okay. So the second type, again, we talked about is, now we've talked about the vertices, what about the edges? The edges are represented by another class called street segment. And basically, again, each street segment is identified by a unique integer ID that goes from 0 to get num street segments minus 1. So any entity in the map, you're gonna find a function in street database API called get num of that entity, which gives you the number of that entity. Yes, a question, go ahead.
Sorry, was that every street gets an ID or every street segment?
That's a good question. So basically, again, we divided the streets into street segments so each street segment connects two intersections, and each of these street segments has a unique ID. On top of that, I'm gonna talk about it in a bit. Each street has its own ID as well. So both of these have their IDs, but they might overlap. I'm gonna talk about what I mean in a bit, okay? Street segments don't have a name associated with them because they are just abstract representation of an edge in the graph. In Toronto, there are around 280,000 street segments to deal with. Okay, so we've talked about that there are IDs for intersections, there are IDs for street segments. Later on, we're gonna talk about the streets as well. All of these IDs can overlap. So for example, if you notice here on the figure here, this node has an ID 0, and this street segment has an ID 0. So you have to be careful in the code to know which ID you are referencing. If you are working with street segments, you need to make sure that this is an ID associated with a street segment. If you are working with intersections, again, you need to make sure that this is associated with an intersection. So how do we do this to make it less confusing as well to the reader? For example, when your TA comes and looks at your code, how do we know that you've used the right ID? Because both of these are integers, and you can swap them. Okay, so it's very easy to get confused. Anyone heard of type defs before? No? Okay. So type def is a concept in C++ that allows you to give a synonym to a certain primitive type so that you make your code less confusing. So you basically write this in your, we've already written this in the street database API so that we make it less confusing for you. So we write type def int street segment IDX. That means I've defined a new type called street segment IDX, but it's actually not a new type. It's exactly the same as an integer, but when you have, for example, when one of the milestone functions that you need to write says one of its parameters is expecting a street segment IDX, that means it's expecting an integer, right? But an integer associated with a street segment. Another type that we've defined is the intersection IDX. Okay, so for example, this is one of the functions that you will deal with, and it's called get intersection name. What it expects is that it expects an integer, but this integer is associated with an ID for the intersection. So this way we make it less confusing to the reader and the writer, and it's less error prone. Part of the code style that you're gonna be graded on is to make sure that you are using the right type. So this still passes the compiler. For example, if you write an int my index, but if the reader comes and read it, basically, what is this? What is this index? Is it an index for an intersection? Is it an index for a street segment? We don't know. So that's why we make sure that you use the right type def and the right variable name. So you can write it as intersection IDX, my intersection IDX. Basically, this is more obvious or more clear to the reader. Okay, now I know that this variable is going to be used as an intersection index later on in the code. Any questions on this? It's a very popular technique in C++ that we use, and you're probably gonna see it a lot in any project that you're gonna work with. All good? Okay. Okay, so we've talked about what our vertices and what our intersections are. Now let's talk about what type of graph it is. Is it an undirected or directed graph? Usually when we deal with graphs, we have to identify what is the direction of the edges. So in an undirected graph, usually we don't put arrows here. That means that if two nodes are connected by an edge, you can get from any of the nodes to the other and vice versa. In a directed graph, however, you can only get from one end of the edge to the next. So you cannot, for example, you cannot get from this node to this node, but you can do the opposite. You can go from this node to this node. Anyone can guess which of these types we should use for our maps? Yes, go ahead. Sorry? Yes, so we have one-way streets in any city in the world, right? So we need to represent them somehow. So that's why we need a direct graph. But what do we do about, if we use a directed graph, what do we do about two-way streets? Yes, we can connect them basically with two arrows. So one-ways will have only one edge, and two-ways will have two edges. But to make it more efficient, we're gonna make it kind of undirected graph, and we're just gonna specify or add a tag to that edge that it is a one-way, so that the user of the code will know that this is not a two-way street. Okay, so when you query your thing from the street database API, you will find several functions as I talked about earlier. For example, get number of intersection street segments. That gives you all the edges that are connected to that intersection. So in most cases, an intersection has 4 street segments. Some of them might have more, some of them might have less. Get the street segments associated with that intersection. So if you know the number of intersections, now you want to basically look at the data associated with those street segments. And then this data is stored in what we call street segment info, which is a struct or a class that we represent in Street Database API. And it has 3 members, the from index, the intersection index that represents the end point of the street segment, and a Boolean that tells you basically whether it is a one-way or not. So if the Boolean is false, you can use the from and to interchangeably. If the Boolean is true, then you can only go from to to, and you have to be careful about using this. Okay, any questions so far related on the Street Database API? All good? Okay. Oops. Yeah. Okay, so we've talked about 2 of the most important types of the entities that you're going to use. We've talked about the intersections, but we haven't covered all of the things associated with those. So we've only said that each intersection will have an ID, a unique ID to identify it, and a name. It will also have latitude and longitude, which will give you the exact point of this intersection on the surface of the Earth. This is for you to deal with when you go, for example, to the lower level API and you want to do more stuff. The street segments will have an index. A speed limit will tell you basically you cannot go over the speed limit on this street segment, and there are some functions that are going to deal with speed limits in milestone 1, but you will mainly use it in milestone 3 when you start trying to find the best or the shortest path from a certain section to the next. A one-way, as we talked about, basically it tells you whether this is a one-way street or not. And there is something called curve points that I'm going to talk about in a second, because not all streets are straight. So some of them might be curved, and we have to represent them with multiple points in the same street segment. And then there is the street end index. The street end index tells you basically which street the street segment is part of. So as I said earlier, and your friend asked, that each street has its own unique ID as well. So sometimes we need to know what street the current street segment that we are dealing with is part of, so we have to do some work on it. Okay, so what about these curve points? Why do we need them? So as I said, not all street segments are city blocks or like straight. So if the street is straight, that's fine. Then we only need one edge to find the, for example, distance between the 2 intersections. But if it's curved and there are no intersections in between, then we have to basically model these street segments with multiple points in order to be able to find, for example, the right direction of the street, the distance between the 2 intersections, because if you look here visually, the distance from these two nodes is smaller than what you have to walk through if you need to go on the street segment. Okay, so each of these street segments has an associated latitude and longitude that you will use in milestone 1, for example, to find the distance between two intersections. Any questions on this? Okay. Yeah, now we've covered the two most important types. The other types are, the first one is the streets. So again, the street is a bunch or a collection of street segments. It's a bigger class than the street segment. And it's also a unique ID and a street name. The street name might not be unique. For example, there are multiple main streets in Toronto. That's why we use integer IDs to identify these. The second type that you're going to use is called points of interest. And these are basically interesting points in the city. For example, a Tim Horton or a McDonald's. These are interesting features in the city that have their own unique index and location, latitude and longitude. And they have a non-unique name again. There are multiple Tim Hortons in the city, so you cannot use the name to identify that point of interest. And the last type is feature. Features are basically outlines of interesting things in the city. For example, a High Park is a feature. Any lake, any stream, any park is a feature. So a feature is identified by a unique ID as well. And the feature type. The feature type can be lakes, parks, buildings, streams, etc. These feature types are defined in your API as enum class. I think you've covered enum class in 244. Okay. So, and then on top of the feature type, there is a set of latitude and longitude points that will identify all of the points of that feature. There are two types of feature, by the way. There is a closed feature, we call it a polygon, and there is an open feature called a polyline. A polygon is identified if the first location or the first point latitude longitude is the same as the last point of that feature. So for example, this pond in High Park is a closed polygon because it goes all the way to where it started. A polyline, however, doesn't have the same endpoint, doesn't have the same first and end point, and it can basically represent, for example, a stream in a park. So like any stream doesn't loop around. That's a polyline. You're going to rely on these heavily in milestone 2 when you're trying to visualize these features, because knowing whether this is a closed or an open will change your code somehow to visualize it. Okay, so I think I've covered most of the things that you need to know in the streets database. I'm going to just recap on what we learned so far. So there are two types of APIs that we provide you and you're going to deal with. The first one is the streets database API. It has 4 types of entities: the intersections, the street segments, features, and POIs, or points of interest. Each of these entities has its own unique identifier, and that unique identifier can only be used inside the city again. It's not a global unique identifier. And it's a small integer that goes between 0 and 250,000. We've made sure that most of the cities that you're going to use, or actually all of the cities that you're going to use, will not go over this number in terms of identifiers. The second type of database that we API that we talked about is the OSM database API. This is again the less organized API and has more data that you might need. It consists of 3 types of entities: OSM node, OSM way, and OSM relation. All of these entities inherit from the main class called the OSM entity. And you can loop and request by a small index. There is also an index associated with these that goes from 0 to 9 million. So you can notice here that this index is bigger than the one used in the streets database API, because it's, again, bigger and less organized. And there is a way for you to actually go back and forth between these two APIs for a certain point, for example. So if you remember, there is OSM data is organized by an OSM ID, which is a very big integer N64 unique identifier for the surface of the whole surface of the Earth. So it's unique to each node across the Earth. And in the streets database API, for each of these entities, intersections, 3 segments, whatever, you can get the OSM ID associated with that so that you can access the underlying data associated with it in the lower level APIs. So you will use this for 2 of the again, functions that you're going to build for milestone 1, and then you'll probably use it when you try to visualize interesting things in milestone 2. For example, some of you might decide that I want to visualize the subway lines, okay? The subway lines are features that are only found in the underlying API, so you might need to rely on the OSM ID to do that. Okay. Questions? This is very important to understand to complete your milestone and future milestones. Okay, so just to recap on what to expect in milestone 1. Basically, you have a list of functions listed in the header file that we provide you. Again, this header file is only readable. You cannot write to it. You cannot change it. And the comments on each function will tell you what you need to do and whether you should expect a performance test for this or not. Okay, and then there will be detailed unit tests. I've provided you with a quick start guide on what unit tests are. Basically, these are tests that are written to test your code based for functionality and performance. There are 2 types of tests that we run. One, the public test that you can run when you write your code, and the other one is the private test. These private tests, again, they are not to trick you, but just to make sure that, for example, you didn't hard code stuff for a specific city, because we need to run your code on multiple cities, and it has to be generic. It is robust against any corner cases that we mentioned in the handout. So we might not test these in the public test, but we will cover them definitely in the private tests. If there is a corner case that you think of that is not written in the handout, that means we're not going to test it, but feel free to write your own unit tests for them. This is actually a good practice for you to learn how to write these tests. In any project that you're going to work with in software, basically you have to write your own unit tests and pass them before actually submitting for your code for review or to merge it into the master branch. There is also one more test that will run Valgrind in the background, and this is just to make sure that there are no memory leaks, there are no memory issues with your code. Okay, I think that's it that's what I have so far for this lecture. If you have any questions, I'm happy to answer. If not, then you've got 3 minutes free. Thank you.